Amplify my voice. Okay, let's go ahead and get started. Presenters are ready, slides are ready, we look good. So um, I would like to welcome you to the last session, the last paper session at AVAR2020. I hope everyone could hear me. If you can't hear me, use sad faces. If you can, maybe a happy face, I don't know, just to verify, but I think we're probably good. Great, thanks. It's good to see folks out there. It's been a great conference. I really had a great time, and it's been really cool to experience this conference in virtual reality, about virtual reality. Um, and despite some small technical issues here and there, I think it's been so much more engaging than some other ways that I have experienced conferences recently in an online format. And so for that reason, I would definitely like to congratulate DigiPen and the organizers, Matt and Lawrence, for organizing a successful conference so far, and thank you. And we have 3 more papers to chat about today. Let's see. The first one is yes. The first one is titled Cloud-Enabled Physical Sound Propagation in Untethered Mixed Reality. Mike Chemistruck and Kyle Storck are here to present their work today. Mike and Kyle are software engineers on Microsoft's mixed reality team. They're currently focused on spatial audio algorithms and room acoustics. And so with that, Mike and Kyle, the floor is yours.
Cool, thanks Keith. And thanks AVAR for having us, and thanks for coming to our talk. I'm Mike. Next to me is Kyle, who'll be presenting with me today, and our third co-author is Nikunj, who should be wandering on the audience somewhere. There he is. And yeah, we'd like to talk to you today about what we think is a pretty cool scenario. And I realize our title is kind of just a lot of words, so I want to paint a picture for you of what we're trying to do here. So imagine here we are in alt space in a virtual conference, but imagine we were in a real world conference with a real conference room that we could actually see each other with. And imagine I handed out a set of AR devices to everyone in the room, maybe some headphones. And then I wanted to have us all participate in a shared holographic experience, complete with fully immersive spatial audio. And we would want everything from accurate acoustics to occlusion, portaling, and everything that you would expect from the real world, but virtually. So what we did here is we created a system that would allow us to do that. So we're going to talk to you today about how that system works. I'm going to start off with a very fast introduction to the 3 effects that we're going to focus on. And then Kyle is going to walk us through how the system works. And we'll end with a demo we have a video of the system working captured from a HoloLens. Now, if COVID has taught us anything, it's that people appreciate when pets walk into your screen when you're doing video chats. We're not doing video chats today, so here are our pets. I'm a cat dad, and Kyle has the dog. The rest of our team here, we have Nikunj listed obviously as a co-author, and the spatial audio team at Microsoft. We have Noel, Keith, Mick, and Ashu, and these guys are great. They've helped us along every step of the way here, so we wanted to give them a big shout out and say thanks. And with that, we're gonna jump right in. So like I said, this will be real fast. I think there's been a lot of talk about the different effects that you can get in spatial audio at AVAR already, so we won't spend too much time, but just to make sure we're all on the same page. I want to start with the sample scene. In our app, we wrote it with Unity, but the system works with, you could imagine writing the system with any app, but we'll stick with Unity. And the sample scene is taken from Unity. It's one that Microsoft uses to demonstrate spatial audio from time to time. So the first thing I want to use the scene to show is called portaling, and it's obviously the path that the direct sound takes to get from the source to the listener. So here you can see that I have the portal path in green, which goes through the open door around to the listener in the bottom right. With portaling, you also get occlusion effects, and here I have just a spectrogram. I marked the volume changes because the axes are actually impossible to read, but also you get different filtering effects as well, so it's not just volume. So we also want occlusion, And the third effect that we want to focus on for our system is reverberation. So obviously big rooms have more reverb, small rooms have less reverb, and anywhere in between, you'll get something in between. So with that, we had to pick a method, an acoustic system. And we thought about runtime methods, we thought about manual methods. It's just some of the ones that we thought of. So we'll start with looking at ray tracing and see if ray tracing is a good fit for what we want. So remember I said I want to hand you an AR device. So I'm not handing you a desktop computer, I'm giving you something like a smartphone or maybe a HoloLens. So mobile compute power. So when we're thinking about ray tracing, we have to think about probably pretty simple things to stay within our compute budget. So simple ray tracing we can do is basic occlusion. These just give you binary values of, is there any obstacle between me and the source that I'm trying to hear? So here you can see on the left, obviously, if the sound source is that sphere, there's nothing in the way, but on the right, there's a wall in the way, so the right source is occluded. And you can do some more here if you cast more rays, but again, that increases your perf cost. You can also do reverb estimation with ray tracing. You can do things like casting rays in all the cardinal directions and trying to estimate the size of the room. A couple things that can get you is if there's open rooms like here, there's the ray that shoots out towards the camera. That'll ruin your room estimation. And also if the source and listener are in different rooms, you have to be careful there because doing raycast at the source will give you a different reverb than if you did raycast at the listener and you'd have to handle that edge case. But again, lots of rays, lots of compute budget, and we didn't want to deal with that because we wanted to keep things working on a mobile processor. So we didn't look at many runtime algorithms. Now, if we wanted to spend time doing things manually, we could use reverb zones. Manually didn't sound fun because we wanted it to scale, so didn't spend too much time here. But if we did want to, this is what reverb zones look like in Unity. Unity gives you spheres you can drag around, and reverb zones, you can assign different reverb parameters inside those zones. And then as the user walks into the zone, you can get those parameters applied. And if you have zones overlapping, it does the interpolation for you. Because Unity only gives you spheres, it's kind of hard to design for like a space like this, where there's a lot of different sized rooms together. You got to drag in a bunch of different spheres. And it's manual, and it only gives you reverb. So again, not really what we're looking for. So we landed at Project Acoustics, which has a pretty big offline compute piece to it. If you're not familiar with Project Acoustics, it is the middleware wrapper around something called Project Triton, which Nikunj has given many talks about at AES throughout the years and other conferences. But we'll walk you through a quick refresher of how it works. So Project Acoustics, you take the scene geometry, you upload it to a compute cluster. Maybe you have a bunch of servers in your closet, maybe you want to use Azure. And you do a wave simulation on your scene's geometry. And you can change parameters of that simulation. You can get more resolution, less resolution, with the idea that the more resolution you get, the more computing power you have to pay for. So you have to find that trade-off of how long you're willing to wait in terms of compute time versus how good does it actually sound. And here I have some debug views. You can see the wire mesh of the geometry, and those green cubes are different simulation points. And I'm going to play a video here, but it has no audio, so I'll just talk over it. This is a video of, is it playing? Of the wave simulation happening. So if you imagine there is a sound source at point P, and it's propagating sound throughout the space, and this is a 2D cross-section of the space. And imagine you have a virtual microphone at place A and place B. You can see on the right here, we have some impulse responses being recorded at those virtual microphones. And we could go and store those impulse responses for every source-listener pair that we care about, but that's a ton of data. So instead, what Triton does is it extracts perceptual parameters out of that, things like the primary arrival direction and the primary arrival power and the reverb power and decay time. And it stores those as a few floats so we can compress it all down. Because for each source, for each listener point, this green cube in the middle here, we have all of these source points, the magenta cubes. And you can imagine we have one listener point every few meters throughout the scene. So this is a ton of impulse responses we'd be looking at. So that compression step of extracting the perceptual parameters out really is a lifesaver. And then at that point, we can use some interpolation at runtime. As the source moves around and the listener moves around, we can get the closest probe points, do an interpolation between them, and get the relevant acoustic parameters for that source-listener pair. With that, we can then take those parameters and drive our favorite spatializer to reproduce the actual acoustic effects of that space. So that's a quick refresher of Project Acoustics. That's the technology we decided to use because at runtime, it's just a lookup. There's no raycast at all. It's very, very fast. Each lookup takes a handful of microseconds, really. So it fits within the budget of our mobile compute form factor, and it gives us something fun that we can play around with. But the hard part is getting it all working in a mixed reality context. And that's where Kyle's going to jump in and tell us how that all works.
All right. Hi, everyone. I'm Kyle. And here are some of the challenges posed to all of us in developing for mixed reality. One, when scanning real-life scenes using AR devices, the captured scans can be noisy and incomplete. AR devices like phones and untethered headsets have limited CPU budget. Also, aligning AR objects and sound simulations across different sessions and different devices is difficult. But we came up with a combination of technologies centered around Project Acoustics that solves these problems and provides a pretty cool experience. So this is a theater at Microsoft that we used as a sample scene. It's got a bunch of chairs, a big wall in front. It's a normal theater, but smaller. So we walked around the theater with our AR device and took a scan of all the surfaces. On the left is a picture of the resultant mesh. The main thing to notice are the holes. It's hard to capture every surface, and that creates these incomplete planes. These holes would be a major problem for performing an accurate wave simulation. To fix this whole problem, we fed our scan through a scene completion service. You can see that result on the left. This took our raw mesh and filled in the holes to create these nice flat surfaces. On the right, you can see that when we put back in the rest of the noisy world mesh, so we did this because this provides useful input to our wave simulation in order to create diffusion effects. One note on this slide, these two bullets should be switched. But now we'll tell you a little bit about the flow for how we managed these meshes. We need that mesh in a few places. We need it on the developer's machine so that we can mark it up and start the simulation. We also need that mesh on the AR device. To make the mesh accessible everywhere, we stored it in cloud blob storage so that it can be downloaded anywhere it is needed, whether that is the developer's desktop or the AR device that they are using. Now that we've got the scene scanned, and we want to be able to share this acoustic simulation with more than one device. Here's an explanation of why this is challenging. So when you launch a Unity application on HoloLens, Unity puts the origin of the scene at the location of the device. That's shown as the first step launch over on the left on the slide. Now say I place an interesting hologram based on that first coordinate system, and the coordinates end up being 0, 1, 2. If I launch the application a second time while standing in a different location, shown as second lap launch on the slides, that interesting hologram would have different coordinates, like 1, 0, 2, in relation to Unity's origin for this specific app run. That is why we use a spatial anchor to lock holograms in place, since that provides a stable coordinate system even across application launches. How the spatial anchor system works is it scans the environment and stores a set of unique visual features. These visual features can be identified later in different sessions and on different devices. These anchors allow the device to orient itself and the holograms it wants to display. We use these anchors to ensure that our acoustic simulation is lined up with the real world on every app launch. But it's still not quite that simple. Alignment is still an issue. This is because when the geometry is exported off of the device, its base coordinate system is a spatial anchor from the device, not Unity's coordinate system. This means we can't just export the geometry and re-import it into Unity, because the geometry will be out of alignment. So we need to export the mesh as well as the spatial anchor's relative transform so that we can recreate that anchor in Unity and get the alignment back. But that's still not enough because the acoustic system is right-handed Z up, but that Unity is left-handed Y up. So we need an additional transform to get the project acoustics data correctly aligned. On this slide, these are two views from debugging. On the left, you can see that the world mesh is nicely aligned with Unity, but then the green acoustic voxels are unaligned. And then on the right, the world mesh and the acoustic voxels are lined up, but then neither is lined up with the Unity coordinate system. So now that we have the data aligned, it's time to do a bake. Here is a video that shows what the Project Acoustics bake process is like for an augmented reality scene. So there is audio in this video. Hopefully you can hear it, but if you can't, you can watch the stream later, or these videos are public on YouTube.
Here I am inside the Unity editor. I'm going to go ahead and use hand simulation to click on the load mesh button and load up into our demo scene, which is this demo water fountain. And go over to the scene view. So I'm going to zoom out a little bit and see that, yes, it did in fact load all the meshes. So we'll expand out over here to take a look at what we have. And each of these is an output from the Scene Understanding API. You got background, wall, ceiling, floor, so forth. And this big GUID in the front just lets us know that they're all from the same space. So I'm going to select them all and mark them all as geometry. I want to do an acoustic simulation on them. And since I don't have a nav mesh, I'm going to mark the floor as navigation. Now here I could go to the Materials tab and design each of the different sets of surfaces with a different material, but I'll skip that and leave them as the default for now. Go to the Probes tab and get this ready to do a bake. So I'm going to say fine, I want the highest resolution, and click calculate. So right now what this is doing is voxelizing the scene and then laying out probes and making sure everything's ready to be baked. So just take a second more here and we'll be off and running. Great. You can see this updated, and if we look at our gizmos, we have a couple little probes that we can see here, and when we move in closer, we've got the voxels popping in too. So that all looks good. Turn these off for now. Go to the Bake tab and see that we have 62 probes, and we have our compute nodes also set to 62. That's just to make things go as fast as they can. So all we have to do now is click the Bake button, wait for that to submit, and then we'll be good to go. We can come back in about 20 minutes and have our acoustics bake should be all set.
All right. Here is another video that gives you an idea of what the wave simulation looks like for that theater scene. There is no audio in this video. So here's a top-down view of the theater. You can see a sound source in the top left. That's where the main theater room is. And you can see the sound waves propagating through the theater room and then making their way into the hallway. You can also see that there's some leakage through the walls. This was because we couldn't get a scan of every nook and cranny of the theater, so there were some holes. But for this prototype, it didn't really matter that much for us. And here's another view of the theater room, a debug view. You can see the flat planes from the Scene Understanding service in blue and beige. You can also see the acoustic voxels in green, which represent the geometry, and the probe points in blue scattered throughout the room. Now, before we get to our demo, we have a couple more overview slides. Here is the technology we used in our prototype. Unity was used to mark up the geometry and schedule an acoustics bake on Azure Batch. We used the HoloLens 2 and its cameras to scan the theater. HoloLens also provides a Scene Understanding API that can take meshes and provide you that nice watertight geometry. The Mixed Reality Toolkit is a suite of development tools for building mixed reality applications. Azure Spatial Anchors is a cloud-based anchor service that allows you to scan a room, place an anchor, persist that anchor in the cloud, and then recall that anchor later on other devices. And then Azure Blob Storage was used for storing our meshes and spatial ID information. And here is the architecture diagram. We can separate this whole system into 3 stages: scanning, acoustic mapping, and client rendering. So we'll start by following the path of the mesh along the bottom. Scanning happens on the AR device, in our case, the HoloLens 2. We scan the environment to get geometric features. We pass the scanned mesh through the scene understanding service. Then the mesh gets used in the acoustics wave solver in the cloud. The result of that simulation, the ACE file, gets stored in the cloud and can be passed to the device. Now, here's the path for a client who wants to listen to that acoustic simulation. That goes through the middle of the diagram. You once again start on the AR device and scan the environment. Using the geometric features you've queried, a spatial search takes place in the cloud and hopefully can find the matching spatial anchor at your location. Using that spatial anchor, a transform can be applied to orient the device so that the acoustic map is aligned up with the real world. Now, the virtual audio can be rendered using the pre-baked acoustic parameters. To sum up, when you put all this together, you get a shared world-locked occlusion system. You scan a real place, bake the acoustics for that geometry, and when you reload the baked acoustics onto the AR device, any virtual sound sources placed in the real world will have accurate acoustics based on the world track geometry between the listener and the sound sources. This includes effects such as reverb, occlusion, diffraction, and portaling. This experience is saved off of the device, meaning that multiple devices can jump in and listen to the same experience. Now for the audio demo. We're going to show a video. This video has audio. The video will start with another view of that wave simulation. Then after that, you will see a live recording taken on a HoloLens inside that theater room. Our baked acoustics are loaded onto that device. A virtual sound source will move around the theater, and the audio will be rendered based on real-life geometry. You can watch the annotations in the top left for information about the sounds that you're hearing in the video.
This produces a simulation which includes parameters such as. In the real world, humans use audio-visual cues to understand the world around them. Acoustics provide critical perceptual cues about the surrounding environment. In virtual worlds, combining spatial audio with acoustics increases user immersion, similar to how detailed wall textures with realistic object lighting do so on the visual side. The approach to acoustics described here is a tool that analyzes virtual worlds.
All right, so that was our system for immersive sound propagation on a holographic device. Thanks for watching. We can take any questions now.
Great presentation. Thank you both, Mike and Kyle, for discussing your work. I guess there should be a question process popping up. Does anyone have any questions? Any hand raises?
All right, Remy, go ahead with your question.
Yeah, thank you very much for the presentation. I was wondering, when you store the reverb or acoustic information, is that information spatial? Like for instance, you mentioned the interest in the modeling diffraction around portals. Is that part of the information you store in the cloud?
Yeah, that is part of the acoustic parameter data set. So for every one of those source listener pairs we were talking about, we have a different set of parameters. So for the portaling, if you're in a separate room from your source, that portal direction will be stored in that data set.
Okay, thank you.
Yeah.
Any other questions?
Well, if there are no other questions, I think let's go ahead and thank our speakers. Thanks, guys. Always love listening to those
Thank you.
demos.
Yeah, they're fun, huh?
Right. We actually wrapped up a little early. I think we've got 3 minutes until the next talk.
Keith, are you speaking? Are you on air? Are you on air, Keith? Okay, I'm still not hearing you, Keith. Is anybody?
Oh, okay.
There?
It was a mic cabling issue. How am I now?
Ah, okay.
Alrighty, next time I'll make sure it's plugged in. Okay, wonderful to see all the smiley faces. All
We're
right,
all back on.
feeling better.
I'll let you introduce
Cool.
yourself, Keith.
All right, great. Thank you. Thanks, Matt. Okay, so it's good to see you all here. It's the last session again of AVAR2020. My name is Keith Godin, and I'm here to talk to you today about fast acoustic obstruction with proximity cost differencing. And I would like to briefly introduce myself because I am also the session chair, so that's what I do is introduce folks. I received a PhD from the University of Texas at Dallas in 2014. Since then, I've been employed at Microsoft working on spatial audio and interactive acoustics. My top favorite products that I contributed to shipping were HoloLens, HoloLens 2, Windows Mixed Reality, and Project Acoustics. And my work has been published at AES conferences, including AVAR, and the Journal of the Acoustical Society and Interspeech. So with that, the floor is mine. So let's see. Actually, my view of the slides is I'm looking at my last slide. But if everyone can see my first slide, can I get a smiley face? Is it all sad faces? I see some sad faces, but I'm also kind of only looking at my last slide. Schutzke.
Keith,
What do you think, Matt?
Why don't you try going backwards on the slides and forwards?
Sure.
I'm also going to reset the browser here.
Let's see, how's that?
Now if you go forward?
Yes.
Yeah.
Oh,
Is this
okay,
your
cool.
first slide? Great.
That is, that's the second slide. That's okay. Here's the title slide. All righty. Cool. So the title slide is the title of the talk is the fast acoustic obstruction with proximity cost differencing. I also Nikunj Raghuvanshi, also at Microsoft Research. We collaborated together on this. Nikunj has been working on acoustic simulation for over a decade, and we collaborated on this project, which is, rather than acoustic simulation, we're looking at lower cost approximations for finding acoustic quantities, in this case, obstruction, which I hope you saw in the last talk, is one of those essential aspects of acoustic propagation, and we'll get into obstruction in more detail as part of the talk. So with that, let's get into the agenda. The agenda, I mean, it's a four-part talk, sort of standard, new algorithms type talk. First, I'll introduce the problem, acoustic obstruction. I'll talk about our proposed new method, and then we'll evaluate the method on some examples, and then discuss the implications for the result. And especially, I plan to spend a little extra time on this section 1, acoustic obstruction, just to talk about the sort of the context of not merely solving some math problems or estimating some numbers, but what is the user impact of estimating or measuring acoustic obstruction in virtual and augmented reality. So, first section of the talk, there's a lot going on in this slide, but really what it's about is sort of introducing the problem itself of acoustic obstruction. Now, that from a user standpoint, it is absolutely essential to full immersion in augmented reality and virtual reality. Why is it? Well, what do I mean by acoustic obstruction? What I'm referring to is simply, at its most basic, is the fact that in the real world, when you are walking around a space, objects, the sound gets louder and quieter depending on the obstructing objects between you and the source of the sound. This is especially prevalent in homes and offices and any space that humans generally occupy that has these walls and partitions and dividers that are especially going to strongly obstruct sound. And we experience it, for example, in this room. In a room that would be like this one in the real world, you would expect to walk maybe underneath the stage as a bar area or that kind of thing. Over there, you can chit chat, and when I say that obstruction is essential to immersion, there's kind of two parts to that. One is that when things don't obstruct, if you have a multi-room experience and you walk sort of into the next room through a doorway or some other kind of portal, the immersion can break when you're hearing a sound coming straight to the wall, like the wall's not there. So it kind of, maybe you notice that. There's an additional dimension to this sort of utilitarian dimension, or maybe related to cognitive load, or maybe even annoyance, depending on the use case. And that is, if you're trying to have a conversation or you're trying to block out sounds, if you walk around, the corner down the hallway or something, and you just can't escape the sound, even because there's no obstruction being modeled, that can actually make the experience more difficult. So, for these reasons, this experience of acoustic obstruction is maybe not just whipped cream on top of your sundae, but it's really essential to building experiences that people can intuitively inhabit and rely on in order to do things like simply have conversations. So that's an important property when you're measuring or estimating or applying obstruction in virtual reality. You can see in this picture that on the left side of the slide. This is a top-down shot. It's of a heat map that shows the sound energy levels throughout the space for a given source location. In this case, the source is, I'm seeing some sad faces, unfortunately. I don't know, maybe not everyone can see the slides, but I can go forwards and back a little. Hopefully that helps, but at this point, I'm not sure if there's anything else I can or should do. But in the case of this room, it's about a house size. Maybe it's like a 1,500 square foot if this were in real life. Specifically, this is the Cliff House from Windows Mixed Reality. So it's maybe a little more open than you would find a house being in real life. But the idea is clear, which is that obstruction as a function of space is smooth. There are definitely distinct areas. You can see, for example, the bottom. I don't know if I could try the laser pointer. I don't know, the bottom of the over here. It's definitely darker. This is this room is isolated acoustically in some sense from the rest of the space. On the other hand, the transition, because it's an open portal, the transition is not some kind of hard cut, right? You don't see a bright line. You see maybe a fast transition, maybe just a meter or something from one region to another, or less than a meter. But it is definitely a transition. It is not something that just simply turns on and off in a binary way. And this, if you're going to model obstruction, it can be useful when sound sources turn on and off. But again, it's a matter of really breaking immersion when you walk through a space and you have sort of a binary nature. So spatially smooth obstruction is sort of essential to a good solution to this problem. So that's the left side of the slide, and I hope you agree that it's an important problem. So moving on then to the right side of the slide. Now here's where we talk about if it's important from a user experience standpoint, how are we going to solve that as an engineering problem? And you have to go both directions with this, is what I'm trying to express here on the right side of the slide. You talk about, it should get quieter, it should get louder, etc. Okay, let's translate that desire into something measurable. And the way you do that is a specific mathematical definition where you measure an impulse or a response or compute an impulse response from a source to a listener location. And from there, we have a well-defined way to say, like, this is the obstruction value for that source and listener pair, computed off of that. So it's a computable quantity. We can measure our accuracy at it if we have something like a ground truth that's either measured or with a way of simulation that is sufficiently accurate. So that's how you go from this. That's how you go from the user experience question to then let's solve this tractable math problem. Then how do you go back the other way? Once I have a math problem, how do I actually integrate that into the software that defines the experience? And there, you can in a straightforward way, maybe just make the sound source louder or quieter. There's some more sophisticated things that you can do, and we actually talked about that last year at a different AES conference on immersive and interactive audio. And the reason I bring this up is because obstruction in this case, as we've defined it, sort of lives with a zoo of a few other quantities on computed impulse response, and then transformed by some aesthetic transformations that allow you to give designer control. So that's how you go from the solution of the math problem or the estimated solution back up to the user experiences. We have additional tools and a framework for that. And that's some of the context for why we would want to solve this problem in a specific way. So that's obstruction, and that's how we're going to frame the engineering research question of how we're going to improve the user experience. So from here on out, let's just get into what it takes to try to get some numbers out and have a good overall solution. Definitely, given that this is so important, not just to augmented and virtual reality, but also to video games and any other 3D interactive experience, there is definitely prior work out there. So I want to situate our work in sort of something of a context. Wave simulation is a way to get maybe something approaching ground truth, depending on the accuracy of your wave simulator. It has high fixed costs, which you can, as we've seen in the previous talk, you can address through cloud-backed solutions as one example, or pre-compute if the scenes are static. But we're looking for something that can handle maybe user-generated content or dynamic content. And there's some other methods. Stochastic ray tracing is also a solution, a very popular solution you can find in the literature. It definitely has merits. The difficulty may be that in order to achieve like spatially smooth diffraction effects that really define like a nice clean obstruction effect, there's sort of this undefined amount of rays that you may need to cast, and it's not really clear at runtime whether the simulation converged or not. Did you cast enough rays, for example? The uniform theory of diffraction is also something that's been explored recently, invented a while back, but it continues to be explored as an applied solution to this problem. And I think the approximations there are really effective. They also maybe don't scale to scenes of the complexity that we're looking for. So it works great if you have a pipeline or a process that generates simplified scenes. But we're looking for a solution that will work on general scenes of arbitrary complexity. So with that, we get to the shortest path heuristic, which you can see there's a great talk at Game Developers Conference from 2016 where they talk about applying this in a fairly popular video game, Overwatch. And the shortest path heuristic is simply you compute two metrics on the source and listener pair in the scene. One is sort of that straight line distance not regarding the walls, and then the other is if I'm going to find a shortest possible path through the scene, connecting the source and listener, what is that distance. So now you have these two numbers, two distances, and you compare them. And if the around the scene distance is much greater, then you would say that it is that the sound source must be more obstructed. It's the basic idea, and it's definitely a heuristic, and it has its merits on certain problems and also its difficulties. So let's dive into that detail next. So for the rest of the evaluation and the talk, we're going to actually look at two very specific failure modes in scenes in general that can make computing an obstruction either an answer or a heuristic difficult. And it has to do with things that are small. Because things that are small, the approximations can sometimes break down, whereas they may work just fine on things that are large. So we're going to talk about what we've termed I think it's already been termed the lamppost problem, which is when you have a small obstructing object, and then the mirror image of that is the pinhole problem, where maybe you have some walls and you have a very small aperture through the walls. At the top row of the slide shows the wave simulation obstruction results. You can see when the sound traverses through a pinhole, it's fairly occluded. The level is much lower. It's quieter on the other side. And then when the sound hits a small obstruction like a lamppost, you end up with just very little obstruction, so there's not much shadow. And some methods, like a single ray hit test, can cast these deep shadows or allow through a very bright line transmission through the space with these hard fades. And then the shortest path doesn't quite have the exact same problems. It works fine in a sense on the lamppost, in the sense that there's really not much of a shadow at all. So at least, you know, these objects don't negatively affect your experience. But then it has problems with pinholes, where there's just allowing way too much energy through the pinhole for the standard shortest path heuristic. So that's what we're going to try to address with our proposed method, is this particular problem of the pinhole problem with the shortest path heuristic. Ideas. We're going to retain the value from the shortest path method, which actually the cost and reliability of the shortest path method are also key. That's why we wanted to build on this. It's very debuggable, which is something they talked about in the GDC talk about on Overwatch, and which is that if you can show the shortest path on the scene, and if it's very intuitive whether that was the right or wrong one, and you have an opportunity to go in and fix. You can add or remove geometry to fix that. So for a user who's not an expert in acoustics, it's definitely something that you can address, or it's intuitive to use. So that reliability in the hands of a user is something we'd like to retain when building a method on top of this. So that's the problem, and so some related solutions and what we'll build on. So now let's get into our actual proposed method for this, which we'll refer to as proximity cost differencing. So there are a few concepts I need to introduce in order to make this, in order to build up this method. One is I want to refer to something called a cost field U. And what is a cost field? Well, it's motivated by this idea that if I'm going to find the shortest path through a space, and I want that path to somehow be quieter or more expensive by going through a portal, well, going through a portal necessarily requires that path to traverse near geometry, right? This is a necessary requirement. And so the idea to address pinholes then is to take the shortest path method, and instead of just computing the raw shortest paths, we'll penalize paths that are too close to geometry. And so we compute this, we define this cost field U, which means that we've voxelized the space, and for every point in space, the cost to traverse that point in space is like low when you're far away from geometry, for some definition of far away, and it gets higher when you get closer. So that requires that we are going to compute a field that actually depends on the nearest distance to geometry. So we'll define something called a distance field D. We have a method to compute that. We apply the fast marching method, which is sort of like a continuous space version of Dijkstra's algorithm. in order to compute the distance field. And then on top of the distance field, we just define what the cost field U is. There are more details in the paper, but the general idea is that now we have a field where if you walk along the field, every time you step on a new element, it's going to cost you more to step on that if that element is near the wall, and it will cost you less to step on that element if you're far away from the wall. So from there, we apply similar concept as the shortest path method, except on this newly defined space. Instead of finding the shortest path through the original geometry, we just find the shortest, we find the cost of the lowest cost path through this cost field, which, the cost field depends on geometry, and the cost is higher when it's close to geometry. And so this way, this example path between a source and listener is going to be more expensive because it has to go through these sort of bright lines near the portal. Okay, that's a rough idea of defining these costs. Then finally, the proximity cost differencing is we're going to compare the cost of traversing that cost field U with a equivalently defined cost field W that involves traversing. The W is defined based on there's no geometry, right? So it's just like with shortest path method where we compared the straight line distance, we end up comparing the cost to the cost field U with the free space cost field. Cool. So that's the method. And now we'll do some evaluation real quick. I know I've got on the schedule, I've just got 2 minutes left, but the evaluation is straightforward. In order to evaluate the method, we constrain the evaluation to 2D, for at this stage. And the ground truth we've defined is the obstruction result computed from a finite difference time domain, or FDTD, wave simulation. And then we've just defined some spaces, 12 by 6 meters simulation region in 2D, and we have a spatial step size of a couple centimeters. And then we chose 3 different frequencies at which we're going to evaluate. One thing I didn't mention is that cost field U can be defined as depending on the frequency that you're trying to model. And that way you can get different effects, different obstruction effects for different frequencies. And the baseline is the shortest path method from the Overwatch paper that we'll compare to as well. So we constructed 2 canonical examples and ran them through this as the evaluation data. The first one is if you have a 1 meter obstruction, and in the top row, you could see the path ratio baseline we're comparing to, and then our extended method, PCD. And then you could see the wave simulation on the bottom row, I believe. Okay, so if you compare PCD to the wave simulation results, there is, as the frequency increases from left to right, you can see that the shadow is deeper, so there's a low pass effect of this sort of this 1 meter obstruction. And then compared to the path ratio method, there is not this like immediate fade in the in the near field from the obstructing object. And then equivalently, we have a 1 meter aperture, and there's, analogously, there's a high pass effect of the aperture, just like in the wave simulation, whereas you don't see that with path ratio method. You don't see a high pass effect, and then the energy, that's because the energy flow is constricted to the aperture, especially for lower frequencies, due to the cost being more expensive to pass through the portal because you have to pass in your geometry. And we have similar results for the 1/4 meter obstruction, where we similarly see a lack of fade, and the 1/4 meter aperture, where we again see the energy flow constricted at the aperture, just like you see in the wave simulation result at 125 hertz. And honestly, out of the results, I think this one is the most exciting, where we see some real progress on the pinhole problem, because the energy flow is constricted to the aperture. There isn't necessarily just this bright line path directly on the other side of the aperture. So discussion, the compute cost for scenes, if these numbers are estimates, order of operations estimates, but we're looking at like 100x improvement versus the baseline wave simulation for maybe a 10 by 10 meter scene. in conclusion, there's an improvement in cost versus the baseline method, FDTD, that has similar benefits in reliability and robustness and usability as the shortest path method. But it also improves over the shortest path method on the pinhole problem. Future work, we need to evaluate on 3D scenes, and maybe there's some new ideas for defining that cost field, and some parameter tuning. And that's the talk. I'd like to thank you for listening, and I'm ready to take any questions.
All right, hand raise button is on the right-hand side of your screen. All right, Remy, go ahead and ask your question.
Thank you for the great talk. I was wondering, you showed how your method improves the rendering of attenuation from the obstruction. I was wondering if you have any thoughts on whether it could, how it would affect the perceived direction of that sound that's being diffracted around the portal.
Yeah, great question. Thanks. I think in this case, we've only modeled and estimated the obstruction effect, not the portaling effect. That would be a separate effect we would need to model. I can imagine straightforward extensions of this method or the shortest path method that would, yeah, you could extend this method to look at that lowest cost path through cost field U, and look at which direction it's coming from, to find out the radiation direction and which one it's arriving, which one it's radiating towards, in order to find the listener loop direction. And you can do either way due to reciprocity. So that you could take this lowest cost method and compute that value. That should be a straightforward extension, I think, of this work.
Thank you.
Yeah, on that note, there's actually, we just had a paper accepted at SCA, a computer animation conference, that looks at doing some of those same computations in 2D for wave simulation results. So there's some methods there for doing that. Might be applied here. Cool. Any other questions?
Any other hand raises?
All right. It looks like those are the questions. So again, I would like to thank you for listening, and enjoy the rest of the conference, including the next paper, which starts in 1 minute. Rashab, come on up on stage.
Right.
Mind your way.
Sorry.
Did I pronounce your name correctly? Rashab, right?
Yeah, that's correct. Thank you. Let me just give me a quick moment so that I can set up my slides in the slide viewer.
Yes, definitely.
I don't see Rishab. Rishab, could you go on air under host tools, click the on air button?
Yes, sure. Let me just first set up the slides real quick.
And then you should probably also select amplify my voice.
I still see 11 folks are viewing my presentation. Oh, they're disappearing. Okay, so they must be all looking at yours. Okay, I think we're about ready. Are you ready, Rashad?
Yeah, I'm ready. Can you hear me now?
I can hear you, yes.
I'm amplified. Can everybody hear me? Okay.
Great.
All right.
Okay, cool. I think we're ready to go. So I'll just introduce you and hand it off.
Sure, thank you.
Yeah, sure. So I would like to welcome you to the last paper talk here at AVAR 2020. Our presenter today is Rishabh Gupta. He is a final year PhD student at NTU Singapore who has worked on different audio technologies for the past 5 years, both in academia and industry for reputed companies such as Facebook and Texas Instruments. His current PhD research focuses on using signal processing techniques and psychoacoustics for achieving acoustic transparency in hearables for augmented reality audio. In addition to the above, he's also worked on research and development of fast individualized HOTF acquisition for AR and VR, and his works have been published in several papers. Amplify my voice. Thank you. His works have been published in several papers in numerous reputed conferences and journals, such as the Journal of the Audio Engineering Society, Applied Sciences, at AES conferences, and at ICASP. So with that, Rishabh Gupta, it's yours.
Thank you, Keith, for the nice introduction. So, good evening, everyone, or good morning, depending on your time zone. My name is Rishabh, and today I will be talking about acoustic transparency in hearables, and my focus will be for augmented reality audio. And in order to achieve acoustic transparency, I will be describing some hear-through techniques and reviewing these techniques which have been proposed in past studies and some of the related challenges. So let me just start by giving a brief outline of the talk. So I will first provide a brief motivation of what is acoustic transparency all about and why is it important for augmented reality. I will follow this by overview of the hear-through equalization technique. This will be a generic overview, and I will follow this up with more specific techniques that have been used in past studies, and giving some examples and listing out the challenges that are faced by in achieving acoustic transparency. I will also provide a summary of the perceptual techniques that have been used, and yeah. So let me just start by I think all of you would agree that augmented and mixed reality is enhancing the way that we interact with the real world by augmenting our senses with virtual information. And we have had very successful products in the market like HoloLens and Magic Leap, which have enabled numerous applications such as gaming, navigation, and multimedia. And these are already being widely used by a lot of people. But in context of audio, what is the desired experience? So if I were to give a very simplified view, it would be the aim to fuse the real and virtual sounds together. And this seamless fusion of real and virtual sounds will be termed as augmented or mixed reality audio. But the question arises that how do we achieve this? And for the context of this presentation and for the context of my paper, I focus on hearables. So how do we achieve this augmented reality audio experience over hearables? So I describe this process into three main signal processing steps, which are listed here. The first is basically the playback of real sounds. Now, if the question arises that in some cases the playback of real sounds is not required because you're not blocking the ears, which is right. But if you are using hearables, in most cases, at least in some frequencies that I'll show in the later slides, there is some attenuation of the real sound spectrum. And that leads to a host of problems that I'll describe later. But what that means is you need to do some processing to compensate for this effect of the hearables on real sound spectrum. And that's where the real sound processing comes in. The second important part is the virtual sound playback, which has been investigated in detail in quite a few studies and also in this conference, but that has two main components. The first is basically an estimation of the local acoustic environment of the listener. where it is really important to estimate this acoustic environment and to encode this information in the binaural rendering engine along with synthesis of the virtual sounds. And only after we have achieved this, along with real sound playback, can we achieve the seamless fusion that I mentioned previously for augmented reality audio. For the purpose of this presentation, I will focus on the first aspect, which is the playback of real sounds in a way that it's perceptually indistinguishable to an open ear listening scenario. So this playback over hearables is, and the techniques used for it, we call them hear through techniques. And the goal of achieving this perceptually indistinguishable playback over hearables from the open ear listening scenario is called acoustic transparency. Okay. And let me just try to provide some motivation of what actually happens when you put on a hearable. So I discussed four major form factors here. So the first one is the personal speaker, of course, which is similar to the micro speakers that are present in quite a few AR devices today. And these do not have a hearable shell, so as to speak, in a way that they do not cause much passive attenuation. So what that means is there's not much need for a hear-through technique in this case. However, even if you have open back headphones, which are considered quite transparent, you do have some attenuation in frequencies, let's say above 1 kilohertz or 1.5 kilohertz, and the attenuation can even be as high as 10 dB in some cases. So of course, the other end of the spectrum is the closed back headphones, and there are various types, I mean, in-ear and circumaural with their own isolation characteristics. But what you see is like about 10 to 30 dB of attenuation in different frequencies. And these headphones are often equipped with ANC these days, active noise cancellation, which can even enhance their attenuation characteristics to about 10 to 20 dB further in lower frequencies, especially above 1 kilohertz, below 1 kilohertz. So the question arises that why do we need to look at these headphones, these two category of headphones, closed back headphones, when we are clearly moving towards transparency? That is to allow the real sound to come through unaltered through the headphones. The answer is that, well, the answer seems counterintuitive, but if you just wait, I will explain why this could be actually a better approach to design a better hear-through system. So first, I will describe to you what the usual approaches for hear-through are. So in this diagram here, I show two cases. One is basically a real sound, the open ear case, where you have the real sound unaltered, and one is with the hearable present. So if you have the hearable present, it looks somewhat like this, where you have a microphone situated at the, I don't know if this is can you see the laser pointer? No. Okay, never mind. So so you can see the, I don't know, I lost it. Okay. So you can see the microphone which is present at the hearable's ear cup facing outwards, which captures the real sound information. And there's an equalization block, and which is followed by the speaker. So what we are trying to do here is basically trying to capture the, oh, I got the, okay. Just let me know if you can see my laser pointer. Is that working? Okay, great. So, and now I lost it again. Okay. Never mind. I'll just do without it. Sorry for that. So so you can see the microphone which captures the real sound information, and the equalization block, which is basically contains the EQ filter or the hear-through equalization filter that contains all the information necessary to translate the captured signal into the desired signal, right? So, so the desired signal at the eardrum, the desired signal received at the eardrum is basically an acoustical summation of the leak real signal passing through the hearable unattenuated, uh, plus the processed real signal which is generated after we have applied the EQ. So we capture the signal at the microphone, apply the EQ, play it back, and that gets added with the leakage that was present in regions where the headphone is not attenuating anything. And that's what you get as D hat. So the aim of, so the, oops, okay. Yeah, the aim of the hear through technique then becomes to obtain a close match of the desired open ear reference and uh, the actual open ear reference, the measured open ear reference, right? Which is shown by the equation here. So if we just plug in the required responses into this equation, the last equation is what we get. We get the we need this information in order to achieve, in order to derive the EQ filter. So we need the open ear reference, which is basically the HRTF. We need the leak real signal response, the hearable response, hearable transfer function, hearable response, and the response measured at the external microphone here, which is denoted by H external. So this is the information that is required in order to derive this EQ filter. So I have summarized the derivation of hear through EQ filters into these three major techniques, namely least squares, adaptive filtering, and parametric equalization. First I'll describe these techniques assuming that I have all the information required, that is the four responses that I mentioned previously, already with me to derive the hear through filter, and then I will tackle the challenges that come in estimating those four responses or measuring those four responses. All right. So let me just start by describing the least square filter. The first approach, which is the least squares filter. So least squares was used by Denk et al. In their paper on acoustic transparency, where they derive the cost function as follows, which if you actually look at it is nothing but the desired reference, which is the first part of the equation before the subtraction sign, and the second is actually the actual measured reference. So, so the cost function basically is represented simply by this, and they solved this during using the least squares approach. In addition to this, they also proposed a few solutions to tackle the various challenges which come in deriving the EQ filters, which I will describe in the later slides. But this was the approach they used. The second approach is using adaptive filtering. And this was actually presented by me in AVAR 2018, where I used an adaptive filtered X normalized least mean square approach to derive the EQ filter. And the primary path, which is shown by H ear here, was actually the ratio of part of that equation. So EQF is equal to HF by H external. So this first ratio is basically H ear, and if you look at it, so all the information I need here from here is basically these three responses. And what's missing here was the leaked real signal response, because we assume that after using active noise cancellation mode, which was done in the paper, the attenuation was more than 20 dB, so the response could be neglected. So this approach showed good results, and we corroborated our objective results with subjective results as well, and it showed a close match for the desired open ear reference. And the third approach is a parametric filtering approach, which has been used in quite a few studies. And the first study which used 3 analog filters in cascade. They call this augmented reality audio mixer. And a similar approach was taken by Ramo and Vesa in their paper, which followed this paper, but they used digital filters instead of analog filters to implement parametric filters for here too. And another study used 4 digital parametric filters instead of 3. Now, you may be wondering why why did they use parametric filters, and how does this work? So actually, a detailed explanation of this will come later, but let me just describe by saying that these approaches were tried mainly for in-ear headphones, where there's a problem which is called the blocked ear canal resonance effect. So if you to put it very simply, and it will follow in the later slides, but just to give you context, it's basically the shifting of a resonance peak. So imagine an open ear response, which has a peak at between 2 to 4 kilohertz, and that peak shifts to 5 to 10 kilohertz in case of a blocked, if your ear canal is blocked by the presence of a hearable, for instance. So these approaches are all trying to correct for that shifting of the resonance peak. So in the first approach, what you see is a first order high pass, which is just to allow the real sound to pass through unattenuated. As we saw, like the real sound up to a certain frequency range will pass unfiltered, and then followed by a biquad peak to introduce the peak at 2 kilohertz, between 2 to 4 kilohertz, which tries to mimic the natural open ear response without the hearable, and then a notch at 5 to 10 kilohertz to compensate for the peak that occurs when the hearable is actually present. So if you have these filters in cascade and you equalize using those filters, basically you're adding the required peak that occurs when the hearable is not present, and you are removing the peak that occurs when the hearable is present. So and a similar approach is actually taken in the next paper for digital parametric EQ, but they use 3 filters instead of 2 filters to remove the peak and add the peak in the hear through response. So in the described approaches, there are a few challenges, and the challenges are mainly due to the fact that if you think about it, all these responses, the ones that I mentioned previously, the open ear response, the response at the external microphone, the response of the hearable, and the leak real signal response, these 4 responses must be measured for each person, for each source location and each hearable position, which is not feasible in practice. So what often happens is there are some measurements done in the lab, and people have tried to tweak those measurements in order to derive the hear through response. And but that encounters certain challenges. So the first challenge is actually matching the processing delay. So in addition to matching the open ear response, we have one more requirement, that the delay between the open ear reference and the hear through equalized signals must match. Else there is going to be problems like audio-visual mismatch, comb filtering, and acausality issues. So what does this mean? So for instance, audio-visual mismatch can occur when the user sees the real sound source, but he doesn't hear the real sound source, because the equalized signal that we have generated after hear through filtering is just not there yet. It hasn't reached the eardrum. So what happens is now there's this dissonance, which can lead to all sorts of problems. So there's no study which has investigated this effect in detail for hear through, but there are studies which have studied audiovisual mismatch, latency, So the typical values, I mean, for hear-through studies for the processing latency for playback of hear-through filters ranges from zero point 0.1 to 10 milliseconds. But then again, yes, these are some of the values, but they reflect more the hear-through system than the actual audiovisual latency. So these are not numbers for the latency. So the second effect is a comb filtering effect. So many of you might be familiar with comb filtering effect as it occurs for loudspeakers. In context of hear through, what can happen is if you are playing back the real sound and you have the leaked real signal or the leaked real sound added to the processed real sound that is playing through the headphone, you can have these sort of comb filtering effects where the two signals get added together. So Ramo and Vesa actually did a study in which they investigated this comb filtering effect, especially for augmented reality headphones, augmented reality audio headphones, and found that at an attenuation greater than 20 dB, so when the leaked real signal was attenuated by more than 20 dB, there was absolutely no comb filtering effect perceptually observed by the. But when the was less than 20 dB, the delay between the leaked real signal and the signal played back by the headphones became crucial. So, so in order to, I mean, Denk in the same paper that was mentioned previously, they tried to compensate for this effect using a regularization approach, frequency dependent regularization approach below 2 kilohertz because the passive attenuation was enough after 2 kilohertz. So the third challenge related to processing delay is actually latency. So this is the equation which is derived from the generic equation which was mentioned previously. And if you notice that the hearable response, the HPF, denoted by HPF, contains a frequency independent group delay with respect to other transfer functions in this equation. So what that means is if this equation is directly used to derive the EQ filter, it can lead to a acausal EQ filter. So in order to correct for this, I mean, there are different techniques, again, depending on the primary hear-through technique that you're choosing. But what has been used in literature has been to add a processing delay in the primary path of the adaptive filter, which the diagram in which I showed previously, and the or in the open ear reference path in case of other techniques such as least squares. So what that helps to do is to basically help to derive a causal hear-through filter, and in case of adaptive filtering, ensure convergence of the filter. Now, for another important aspect of hear-through filtering is the directionality of the different responses. So as I mentioned, except hearable response, all other responses have some sort of directionality which depend on the characteristic of their sound source, their location, type, etc. So my study was based on, my previous study was based on an hypothesis that if we included different hear-through equalization filters for each direction using the adaptive filtering approach mentioned previously. And what we found was it actually performed better than the averaging approach, which is typically used in headphones. And we compared it with the Sony 1000XM2 headphone that was available, and it showed better performance. And for each direction. And you can clearly see the gains in mid and high frequency, where our proposed approach shown in red outperforms the traditional state-of-the-art approach shown in black for almost all angles, for all angles. So we extended this approach for multiple source scenario because usually in real settings we have multiple sources, and we also incorporated a direction of arrival estimation block because obviously a direction hear-through filter, which is based on filtering based on direction, would require such a block. So we used a neural net approach to estimate directions, and this neural net used features derived from binaural signals such as IACC and ILD, which has been shown in literature to show good DOA performance. And the whole system actually was tested for real signals as well as different kinds of synthesized signals, and showed quite good performance. The spectral difference was about 2 to 3 dB for each direction. So, but there have been other approaches as well. So, in a study by Patel et al., they used beamforming along with ANC to do directional filtering, and with the added advantage that they used that it also caused a reduction in the ambient noise levels while enhancing the hear-through capabilities in the desired direction. So, the last challenge for hear-through can be basically summarized as personalization, because because as you see from this equation, all these four responses, href, hleak, hexternal, and hpe, are actually idiosyncratic, and except href, they all depend on the fitting of the hearable into the ear. So although there's no study for estimation of the response at the external microphone, which is H external, there are few studies for modeling of leaked real signal. So there has been study by Tekender et al., which used a lumped element model, and there's another study which used warped LMS to estimate this leakage. So I'm just running out of time, so I'm just gonna fast forward the presentation a bit, but I hope you can follow. So there have been other approaches to model hearable transfer function as well. These are the three main approaches, and we have actually proved in a study like in case of virtual auditory displays that HETF can the hearable transfer function can also cause front-back confusions and temper differences in hear-through, like it does for binaural rendering or virtual auditory displays. So the same techniques apply, which can be used to model in that case. And the last one is basically approach for tuning of non-individualized filters. So you can also personalize hear-through filters using manual tuning or tuning based on individualized measurements. And this comes back to the to compensating for the effect of the blocked ear canal resonance that I explained previously. So basically, blocking of ear canal leads to pressure chamber effect, where the peak for 2 to 4 kilohertz, which occurs for open ear, gets shifted to 5 to 10 kilohertz in case of blocked ear canal. And as described previously, people have used biquad peak and notch filters to compensate for this effect. This is a table to provide the summary of whatever I just described. It's the same table in the paper as well. And just the last point I'll make here is this is the table for perceptual techniques. And mostly people have used either AB or Mushra tests to judge the overall sound quality or specific attributes such as spatial or timbre. There has been only one study which has tried to do a long-term analysis of the usability of such hear-through devices, and people have rated day-to-day activities based on mean opinion scores such as eating, drinking, walking, chewing, and there are quite a few interesting conclusions from that study as well, which you are encouraged to look at if you're interested. And that's it. So my aim for this paper was to provide a generic description of these hear-through techniques and their challenges, along with the perceptual tests that have been used in past studies. And there are quite a few unsolved issues for deriving hear-through filters, a few of which I covered in my slide, but I'll just reiterate that there are no perceptual studies right now which have investigated the effect of audiovisual latency for hear-through, and there's still work ongoing even in on my end to investigate hear-through filters for different acoustical scenarios, like we did for multiple sources. and also for accurate estimation of individualized responses. So I mentioned that we need accurate estimation of those 4 responses, and that's also ongoing work. So thank you all for listening. That's all from my side. If you're interested to know more, you can reach me on LinkedIn or ResearchGate. Thank you. These are some of the references. Thank you. Thank you.
Any questions from the audience? Thank you for the great presentation, by the way. That overview, fascinating area that's very relevant.
Keith, could you amplify your voice again? Sorry.
Oh, yes, definitely. Thank you for the reminder. Yeah, thanks again for the talk, Rishabh. Fascinating overview of an area that's essential to augmented reality. Oh, my microphone. Are there any questions from the audience? Oh, we have some. Great.
All right, so David, go ahead and ask your question.
Hey Rishabh, this is David from Facebook Reality Labs. Thanks for the nice presentation. I was just wondering regarding the matrices that you showed for measuring the error of the headphones EQ. Is there anything about how to weight the different frequencies?
Sorry, David. So you are asking about the error, computing the differences between the different EQs. Is that correct?
You showed on slides 11 and 12 2 approaches for measuring the error between the referent pressure and the...
Is this the slide?
Yeah, this one and the next one. So I was just curious if you have any thoughts or work on how to average across the different frequencies, how to weight different frequencies for this application.
I see. Okay. I think I get your point. And actually, I think, are you referring to this? Let me just. Is it? Okay. Is it this curve? I mean, for instance, so here I will, for example, I computed the error between different EQs, and this was averaged for 3 frequency bands, over 3 frequency bands. So, I mean, this was just like I call that like low, medium, high. So that's like 0.1 to 1 kilohertz, 1 to 5, and 5 to 16. So if I understand your question correctly, you are asking what's a good way to average across these frequency bands? Is that?
Yeah, for example, I just wanted to hear your thoughts about what is a good approach to average the different frequencies or different frequency bands.
Yes. So, I mean, there have been a few approaches, and I think this is a this is a good question, because it's also one of the problems that we have, that computing the spectral differences, for instance, among different curves, right? And how to do it effectively among different frequencies, because you are absolutely right that we see so much variation, especially in EQ, that sometimes this, for example, this plot won't show you the correct picture, right? So I think what I tried to do here was to notice where the maximum variations or the inflection points were, and to divide it into, sort of like discrete bands, like 3 bands, 3 major bands. But of course, people have tried sub-band approaches or ERB band approaches, which I think might be better perceptually. But yeah, I mean, it's still, I think it's a good topic to explore further as well.
Okay, great. Thanks, Rishabh.
Yes. Thank you, David, for the question.
Remy, go ahead and ask your question.
Hi, this is Remy from Magicube. Yeah, thanks for the great talk. Sorry if maybe you mentioned it, I missed it, but I was curious. You mentioned how latency is potentially a challenge. And I was wondering what kind of latency you managed to achieve with your system, the one you presented toward the end that includes the direction of arrival estimation.
Yes. So our system currently does not include, I mean, so we don't have a real-time system with the direction of arrival integrated. We are still in process of, I'm still in process of building that. But the system that I have for here through is also something which I have not published, but I can tell you that, I mean, right now I'm just investigating different latencies and trying to see what. So usually, I mean, we can use ANC systems for reference. So ANC is able to achieve microsecond latency for the processing. So I mean, so right now my goal is to go as low as possible, basically. So I believe that anything in the microsecond range should be good enough for here through as well. But as I said, it's an open question which will depend on the three factors that I mentioned. So you should be able to have no audiovisual mismatch, and the comb filtering effect shouldn't be there. So since there's no reference in literature, I can't really say what's a good ballpark number for that.
Okay, thank you.
Yes. Thank you, Remy.
All right. I think are there any more questions? Doesn't look like it. Okay. With that, I'd like to thank our speaker again. Thanks for the great talk. And that is the end of this session. And it was great seeing you folks here at AltSpace, in AltSpace for AVAR. And I hope to see you all again soon.
Yes. Thank you, everyone. Thanks, Keith, and thank you all the organizers for AES. Thank you.
Thank you all for coming. This was really fun, and as always, you're all welcome to come and join us back in the AVAR lobby for some more chat. I hope to see you soon.